With an increasing prevalence of lithium-ion batteries and the lack in lithium extraction infrastructure, the current supply methods are falling short for this metal. In response to this problem, Life Inc. has developed a hydrometallurgical process to recover lithium through recycling spent batteries. My work focuses on the removal of the primary process contaminant, which is aluminum. The first stage of removing aluminum is designed to selectively leach it using sodium hydroxide solution. I have modeled this reaction in a CSTR where the reaction is taking place between the liquid phase of excess dilute sodium hydroxide and solid aluminum. The particles of aluminum in the battery feed were modeled as spherical, non-porous solid particles possessing a native oxide film. As such, the chemical reaction is considered between this oxide layer and the sodium hydroxide, producing soluble sodium aluminate under a first-order reversible reaction model. In the bulk of the sodium hydroxide solution, the reaction rate is proportional to the available surface of the unreacted solid. So I selected the use of the shrinking core model, where the reaction rate is controlled by the chemical reaction only. A second shrinking core model was also investigated. Here instead, the rate of the reaction is controlled by diffusion across a solid product layer shown in green to access the unreacted core below. Since this model resulted in the formation of solid hydroxides, it failed to provide a soluble aluminate product. So we stuck to the original chemical reaction control model. Once the kinetics of the system were understood, I then justified the constant shrinking layer of oxide. Literature suggests that the oxide is able to reform rapidly due to aluminum and water in the solution reacting at a rapid rate much faster than that of the alkali reaction. Because of this, the oxide layer is described as a self-limiting factor where the solution becomes unable to diffuse through the oxide layer to the pure aluminum as it's growing again to a constant thickness. So the overall reaction is involving two simultaneous steps of aluminum reacting with sodium hydroxide and then also reforming the oxide layer. The kinetic modeling of the alkali leaching system is essential to refine the current process design and ultimately improve our overall process for the recovery of high-value recycled metals, which is directly impacted by the effective removal of the aluminum contaminant.